Okay, here we are again, continuing our discussion about the wonderful world of logs. There's a little math humor right here. It's logs. Okay, so y'all, we have not talked too in depth about graphing logs. We hit on it just a scotch back in section 4.4, so if you want to go back and look at your notes there, that would be grand. I did just want to talk briefly about it, and again, since we're all sitting here enjoying a lovely 17-day weekend, I figured I would make a quick video about it. So, I'm going to talk about graphing logs first, and then I'll take a quick look at supplement 4.4. So my question for us to get started is, do you remember what the domain of a logarithmic function is? So here for your amusement is a logarithmic function, f of x equals log base 2 of x. Now, it's hard to think about the domain just looking at this, but if we change this to exponential form, so this means, first of all, I'm going to substitute this guy for y. So this means 2 raised to the y is equal to x. Now, note a few very important things. Number 1, 2 is our base, and as such, 2 is a positive number. Let me ask you, is there any exponent that you can think of, if we apply it to 2, will result in a negative number? Your answer should be no. There are no exponents that would result in x being a negative number, so we know that x has to be positive. The next question is there an exponent that exists such that x would be equal to 0 exactly? Again, your answer should be nay. There is no exponent that exists that would make x 0 exactly, which means our domain for this guy right here would be 0 all the way up to positive infinity. X can be anything else above 0, but it has to be positive and it cannot equal to 0. Now, while we're here, let's talk just a scotch about the range. Take a look at that exponent right there. That's going to be our range. What values can we put in for the exponents? Can we have negative exponents? You bet your boots we can. Can we have decimal exponents? Absolutely. Can we have positive exponents, fractional exponents? All of these things are fantastic. So our range, for that reason, will be all real numbers, or in interval notation, negative infinity, all the way up to positive infinity. Okay, now that we've gotten that conversation out of the way, let's actually talk about graphing. All right, so here is that same function, f of x equals log base 2 of x, and we are going to graph it. Now, again, what I would encourage you to do is to think about this function like this. Y'all, it is hard to write and talk at the same time. I just want to let you know it's a struggle bus over here. So what I'm going to say, this is going to be 2 to the y is equal to x. I'm changing this a little bit because this makes more sense to me than this guy over here. So I'm going to look at that while I am graphing. Now, as in all graphs, what I'm going to do is I'm just going to make myself a table. So here we go. But I'm going to do it slightly backwards. So bear with me. I'm actually going to write this guy over here. So 2 to the y is equal to x. I'm going to do this slightly backwards. I'm not actually going to plug in my x first. I'm going to plug in my y first. Again, just because if I plug in my x, with like our usual 0, 1, 2, 3, 4, it's going to be a little bit difficult for me to come up with the exponents that equal to that. But if I plug in my y, it'll be easier for me to identify the x that corresponds to that. Now, please note, I'm not saying that my y is the independent variable. That's not what I'm saying. But for our purposes here, it's going to be a lot easier to calculate what x corresponds with y on the graph. So here we go. I'm going to say, let's start with the easy one. Let's say 2 to the 0 is equal to 1. So when x is 1, y is 0. Make that a 0. Let's go further. 2 to the 1 equals 2. So when x is 2, y is 1. 2 squared equals 4. So when x is 4, y equals 2. You follow me? We're feeling good? Rock and roll? Actually, I'm going to actually go backwards. This is terrible mathematical practice, but I'm actually going to go backwards to 2 to the negative 1, which would get me 1/2. So when x is 1/2, y must be equal to negative 1. I think that's a good set of points for us to get started with. Now, I'm going to go over to the graph. Now, what we talked about on the last slide, if you recall, go back and take a look if you want. I don't mind. What we said is that the domain of this function was going to be 0 all the way up to positive infinity, with x not equaling 0. As such, my friends, we should probably imply on our graph that we know that that domain is all positive numbers, not including 0. So what I'm going to do is I'm going to go ahead and draw an asymptote going down the y-axis like that. Let me see if I can make that a little bit thicker so we can see that. Ba-boom, ba-boom, ba-boom. There we go. Okay, so I'm going to go ahead and draw an asymptote. I had to make this comment on many of your exponential tests. If you know that there is an asymptote, please draw it in because it helps me to identify the rest of your graph. Okay, so I know that there is an asymptote there at x equals 0, and x cannot cross below that because my domain is all positive numbers. Now let's just graph some points. Let's go ahead and graph. So 1 comma 0 is right there. 2 comma 1 is right there. 4 comma 2 is right there, and then 1/2 negative 1 is right there. So we begin to see our curve take shape. It is a curve, so it's gonna look kind of, oh golly, oh well, pretend like I passed through that point. My digital skills are imperfect, so, oh, okay, I'm embarrassed, but just pretend like it crossed through that point. Now remember, this graph is going to be the inverse of the exponential graph. So if we drew our y equals x line diagonally through there, we would be able to see that. But that's a conversation for another time. That's what we did in section 4.4. So if you want to go look back there, you can see that. Now, what I would like to do before we move on, we have this lovely graph. What I want to talk about right quick is transformations. We have had a lot of difficulty, especially on that last test, with transformations. And I'd like to talk about how to do those. So let's say, I'm going to move that guy out of there. Okay, let's say we had a new function, and let's call it, not f, nope, sorry, I've got to undo. Okay, let's call it, I know, g of x is equal to, let's do 2 log base 2 of x plus 1 minus 2. Let's do that. Okay, now what we're going to do is we're going to apply these transformations. Now, please don't, this is what a lot of folks did on your exponential test. You went to your calculators and you tried to plug in a bunch of this stuff. You plugged in an x and you tried to get out a y value. If you do that, you're going to get some bonkers numbers. Don't do that. You don't have to do that. Don't make it more difficult for yourself. What we're going to do instead, because you won't have a calculator on this part of the test, is we're just going to apply these transformations. So let's think about what each one of these means. This 2 out here, it is not with the x, which means it's applied to the y. What are we doing to the y? We are multiplying y by 2. Yay! All right, what about this guy? That is with the x, which means we're applying it to the x. Since it's with the x, it's the inverse, it's the opposite inside, so we're not adding 1 to x, even though it looks like we are. Y'all, what are we doing? We're subtracting 1 from x. It's a from. Okay, and then last but not least, this guy right here, that minus 2 at the end, is it with the x? Is it in the parentheses with the x? No, which means it's going to the y. So that means we're going to subtract 2 from y. So what I'm going to do is I'm just going to take my table here, I'm just going to extend it a little bit. I'm going to have my x sub 2 and my y sub 2, and I'm just going to apply those changes. So the only change I'm doing here for the x column, the only change is I'm subtracting 1 from all my x values. So 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 1 is 3. And 1/2 minus 1 is negative 1/2, or negative 0.5. Okay, now let's move to the y side. Remember PEMDAS, order of operations, which means we must do this multiplication part before we do the subtraction part. So let's start with the 0. 0 times 2, surprise, 0. 0 minus 2, minus 2. 1 times 2, 2. 2 minus 2, 0. I hope you can see what I'm doing since I'm not writing it down. What I'm doing is I'm going up here and multiplying y by 2, and then I'm subtracting 2 from that value. Order of operations. 2 times 2 is 4. 4 minus 2 is 2. Negative 1 times 2 is negative 2. Negative 2 minus 2 is negative 4. Alright, before we start graphing, let's think about this asymptote. Is it affected by the x values or the y values? I'll give you a second to think about that. Think. If you said x values, you are correct. It is affected by the x values. How did I change the x values? I shifted them left by 1 unit, which means my new asymptote is going to be shifted left 1 unit from there, so it's going to be over here at negative 1. So I'm going to go ahead and draw that in, so there's no, I'm so sorry y'all, my drawing is not the best on these things. That's okay. Okay, now let's go ahead and just do some graphing. So 0, comma, negative 2, that is my first point. So I'm going to put 0, comma, negative 2 right there. 1, comma, 0, that's my next point. That goes right there. 3, comma, 2, that's my next point. That goes right here. Negative 1/2, comma, negative 4. That's going to go right there. Let me see if I can draw this without messing up too bad. I mean, kinda. Not terrible. A couple of things on the graphing, y'all. Please note that I'm extending the graph to the edge of the graph. I'm extending the line, to the edge of the graph, and I'm putting arrows on both sides, implying that it continues forever. Now, let's look at what we've got. Does this make sense? Look back up at the transform function. This guy means I am stretching it vertically by a factor of 2. This guy looks a little stretched out. He's going up a little higher. This guy, this negative 2 at the end, means I shifted down 2. Looks good. This guy means I shifted left 1. Did I do that? Yes, I did. So, this looks good as a transformed function. Please, please make sure that you know how to do this without a calculator. I repeat, without a calculator. Okay, we're going to move on to the supplement on the next slide. Here we go. Okay, friends, here is the supplement section 4.4. The question states, the graph of f of x equals log base a of x is given here in figure 18. Oh, find a. And then it says, note that the points 1, 0 and 25, 4 are on the graph of f. Pro tip, y'all, 1, 0 is going to be on the graph of every single logarithmic function you see because if you think about it, log base a of 1, a raised to what power, anything raised to what power will always give you a 1, and the answer to that is 0. Yay. So that that point will always be on the graph. The other point is the point that we are interested in. Now, please note that our asymptote is still at x equals 0, our little vertical asymptote. They haven't drawn it on there, but you can see the graph kind of start to taper off and head down to negative infinity right around that spot, which means there's an asymptote there. Now, what we need to do, since they are implying by giving us this general form right here, I don't see any transformations. So it looks like there's not going to be any shifts, left, right, up or down, or stretches or compressions. It's just going to be an old-fashioned regular function. So let's look at what we know. We've already said we know this guy, log base a of 1 equals 0, but that doesn't matter because that goes with every single function. That's not going to help us find what a is, because if you think about it, if you write that out in exponential form, you're going to have a to the 0 equals 1. That doesn't help me at all, because everything raised to the 0 power is equal to 1. Wah, wah. Okay, however, this other guy, this 25, 4, that's going to be very useful. Because what I can say here, let me plug that in. I'm going to say, okay, so 4 equals log base a of 25. I'm just using this form right here. I'm just plugging in my x and y to that form right there. Here is the y, here is the x, if you were confuzzled there. So let's rewrite this in an exponential form. What this means is a to the 4th power is equal to 25. Y'all, I only have one calculation to do to figure out what a is. Anybody? Anybody tell me? Anybody? Anybody? So many hands raised. Since there's nobody actually raising their hand here in my house, I'm going to answer the question, which is, you're just going to take the 4th power. That's all you have to do to undo that little guy up there, this little guy right there. So I'm just going to take, not the 4th power, did I say that out loud? I meant the 4th root. That's what I meant. So my exact answer would be a is equal to the 4th root of 25. If you wanted to go cray and find the approximate answer, you could say a is equal to 2.236. There's a lot more numbers after that, but I'm going to stop right there. And voila, that is a. I'm done. Piece of cake. Booyah. Let's do the next two. All right, hopefully what I would hope that you would do with these guys is go ahead and just, if you want, give it a try on your own. See if you can do it by yourselves. I think you can. I have faith in you. And then come back and check. I'm going to work these through pretty swiftly. So, yeah, go do yours. Pause this because I'm not going to wait for you to do it like right now. But pause it. Go do these if you haven't already, and then come back and check your work. So here we go. I'm going to start with number 2. I have a table of values. Please note the 1 and 0, always there because it's a logarithmic function. I can't use those, but I can use any other one. So on the number 2, I think I'm going to use this guy just because it's got 2 whole numbers, and I like whole numbers, so I'm going to go with that. Again, my base function is just log base a of x. Doesn't look like there's any transformations going on. So I'm just going to use this point right here, my x and y, and plug it right in. So I've got 2 equals log base a of 400. Y'all, I keep not being in the habit of putting parentheses around the arguments. You should always put parentheses around the arguments as a matter of formatting. So please take that into account. I'll try to get better at that. Okay, I'm going to write this in exponential form. So this means a squared is equal to 400. How can I get rid of that square right there? By just taking the square root. So A is equal to, I believe the square root of 400 is 20 exactly. So that is both our exact and our approximate answer. Booyah! All right, let's look at number 3. Número 3. I'm not going to use 1 and 0 again. This looks very nice right here. This looks great. I've got whole numbers, small whole numbers, so let's get to it. Here is my original form of the function. I'm going to plug in the x and the y, so that's 2 equals log base a of 3. There we go, parentheses around the argument of 3 there. And let me just write it in exponential form. So a squared is equal to 3. And to get rid of that squared, I'm just going to take the square root. So a is equal to the square root of 3. And that's it. That's your exact answer. Again, if you wanted to get crazy and show off to your friends, you could write a is approximately 1.732 and a bunch of other numbers. I will specify on the test what I'm asking for, exact or approximate. Okay, y'all, that is all I have. If you are still watching, you shall be rewarded with this picture of an ugly cartoon cat who loves math just as much as you do. I love math. There you go. Okay, y'all, I will be answering any questions that you have about this whatsoever. Please send me an email if you have any questions. Otherwise, hopefully, I will see you before too long. Okay, peace out.